Hey, AP Chem. We are going to be taking the weak acid, weak base pH problems and kind of flipping them on their head a little bit. With this section of Unit 10, we are going to be taking data that is given to you in a problem and finding the Ka and Kb values from that data. Now, when we did equilibrium problems kind of right at the beginning, we're talking like back in Unit 8 at this point, we did this. So I gave you enough information and you could find the K value. Well, in this case, that information sometimes isn't necessarily as straightforwardly given to you as it was in those problems. And so we've got to kind of pick that apart a little bit. So the big question with all these is, how the heck am I supposed to do this, obviously? And when you want to get a numerical value for K, given some sort of data, obviously you need to know all of the missing pieces for the information that shows up in your equilibrium expression. So for instance, if I have the reaction of nitrous acid, HNO2, in water, it breaks into the nitrite ion, NO2-, and H3O+, our hydronium ion. If you think about this reaction, think about what your Ka expression is going to be. So I want you to stop and kind of mentally think about what that Ka value, not the Ka value, the Ka expression needs to look like. So think about what that'll look like, pause it if you need to, and then I'll show you what it is, okay? All right, so here's our expression. It is the concentration of NO2- times the concentration of H3O+ divided by the concentration of HNO2. Remember, this is all at that equilibrium point after our reaction has kind of settled into its equilibrium position. So to find that K value, I'm going to need to have the NO2- concentration, the H3O+ concentration, and this. So I need all three pieces. Where are we going to find that? Where in the problem are they going to give me all of that information? And so realistically, in the problem, they are going to have to give you an initial concentration. They're going to have to tell you it's an X molarity solution. That's not something that you can generally divine from that. They could give it to you directly in the problem, or in theory, they could make you do a titration problem too. That seems a little sadistic, but you never know. So they could do a titration and ask you to figure out the initial concentration, and then that could be the way that you get that initial concentration. So, again, that would be kind of mean, but they could do it. They could give you the concentration of the conjugate at equilibrium, or they could give you the pH. So let's go back to our expression from earlier. So initial concentration, if they tell you it was a 0.5 molar solution, that is going to be your denominator. And if you think about our ICE tables that we've kind of set up, it's always been X squared over that initial concentration. So if they give you that initial concentration, that's what you're going to put right there in your equilibrium expression. And like I said, most of the time, that is going to have to be given to you. Now, they could give you the concentration of the conjugate at equilibrium. So they could say at equilibrium, the nitrite concentration is found to be X or whatever. They could tell you that number. What happens is you have to remember that in your balanced equation, whatever the concentration of your NO2- is, if we're talking about just a plain acid or plain weak base, that concentration is also equal to the H3O+ at equilibrium. So if I know the nitrite, I also then know the H3O+. Okay, so if they give you that concentration, technically they're only giving you one piece of information, but they're actually giving you two. And the same thing happens with pH. And honestly, pH is the one that's the most work, unless we do that titration thing, which again, don't think that's going to happen. What happens is if they give you the pH of solution, they have indirectly given you your concentration of H3O+. So you get that concentration. And again, remember, because of your equilibrium expression, the NO2- and the H3O+ are equal. If they give you the pH, you can find your H3O+ concentration, and then that is equal to NO2-. That's the X. So X squared is going to be your top part. So in the problem, they are going to probably give you the initial concentration more than likely, and then you're going to have to work to figure out that concentration of X and then recognize that X is equal to both of those values. So what we're going to do is we're going to work through an old FRQ from an exam because it does a good job of kind of reviewing a couple different concepts we've talked about so far, and then ties in this new K expression thing. So here is the KA problem that we're going to kind of work through. So this is the 2014 exam, and it gives us a reaction between this crazy huge substance and water. We look at it, and if you follow the reaction, you should be able to tell right away that this is an acid. But if you don't feel like doing that, you can read literally the first two words, and it says propanoic acid, and it tells you the formula. So we match up here. Is a carboxylic acid that reacts with water according to the equation above. Ta-da! Okay. At 25 degrees Celsius, the pH of a 50 milliliter sample is 0.2 molar propanoic acid is 2.97. So if you see here, like they've kind of given you some of that information to fill that in. And so what we're going to do is we're going to work through the different problems here just to give you a feel of kind of how this is. Now I cut out C1 because we haven't technically talked about that. We're actually going to talk about that in the next couple lessons, but you'll see kind of how they really like to interweave and overlap a lot of these concepts. So I am going to get into the doc cam so we can kind of write some stuff down, and then we will get cracking on this. All right. So question A tells me or asks me to identify a Bronsted-Lowry conjugate acid-base pair in the reaction and clearly label which is the acid and which is the base. So if we look at our combination here, and you remember your conjugate acid-base pairs, you got to identify your acid, your base, your conjugate acid, and your conjugate base. So if we look at our reaction here, our acid is going to be this guy here, because they tell us it is, and that makes H2O our base in terms of Bronsted-Lowry terms. This guy here comes from the acid, so that makes this the conjugate base, and H3O plus is going to be our conjugate acid. So when they talk about an acid-base pair, they are talking about like the parent molecule and then the child, the conjugate here. They are not talking about this. So it's a conjugate acid-base pair is always this combination or this combination. It's the thing and what the thing turns into. So for A, what I'm going to do is, and I would not be confident that this labeling would be enough here. So what I'm going to do is I'm going to identify a pair. So I'm just going to put my formulas here, CH3, CH2, COOH, and I'm going to label that as the acid. And then I'm going to put down my conjugate. And that's my conjugate base. So that is one pair. That would be worth 1 point. And then the other option, you don't have to put both, but know that they're both correct. You could put H2O as your base, and then H3O plus as your conjugate acid. So both of those would be fine, and you have to label them to get those points there. So that is question A. B then is our actual problem. So it says to determine the Ka for propanoic acid at 25 degrees Celsius. So we do not have that Ka value, but what we do know is that the Ka is equal to, and I'm going to have to kind of keep sliding back here. Remember this reaction. So my Ka is going to be equal to that conjugate times the concentration of H3O plus divided by the concentration of my original acid. And you ask why they write such a long chemical formula here. But when they ask you to find a K value, always, the first thing you want to do is you want to write that expression, because that is going to be giving you a hint as to what kind of information you need. So I need all of this stuff here. Now, if I look and read carefully in the start of the prompt, it tells me that initial concentration is 0.2. So I know that whatever that number is going to be on top, it's going to be over 0.2 molar. And I don't know why I put that M in there because we never have numbers in there. But that's our concentration of this acid here. So what I have to be given in this problem is these two concentrations. And of course, they don't give it to me in a straightforward manner. What they do is they give me the pH. But if I know my pH is 2.79, okay, I can figure out my concentration of my H plus or H3O plus, you know, they're the same and interchangeable, by taking 10 to the negative 2.79, and that is going to give me that pH number. Now remember, or that H plus concentration. Remember, you cannot use this as the answer. You need to get a number out as some sort of decimal form. And when I do that, I get 0.00162 molar. Resist the urge to round this too much. I like to keep at least 3 significant digits here so that I can really make sure that my number isn't rounded off too much until the very end here. So I've got that number. Now, because of my knowledge of how ice tables work, I know that that is equal to my concentration of my H3O plus, and it's equal to the concentration of my conjugate, the CH3, CH2, COO minus, again, the longest formula in the world. They're the same. And that is equal to, if I remember, X. Okay, so when I set up my equilibrium expression, a lot of times this is set up as X squared when I'm finding my pH, but now I know my X. So what I'm going to do is I'm going to put those both in 0.00162, and I'm going to square them. And if it makes it feel icky for you to put it in as a squared, you could put them in separately, but it does the same thing. Okay. Then it's just a matter of plugging and chugging. So I'm going to put these numbers into my calculator, and I get a K value of 1.32 times 10 to the negative fifth. That's my K value. So even though they weren't necessarily super straightforward with the information, they did give me enough information in the problem to find my K value there. And this is a common thing that you see on the FRQ. So this is a skill that I think you need to be aware of. There is always enough information for you to be able to answer the questions. So it's not like they were just like intentionally leaving you with nothing. It's there. You just have to figure out how to deal with it. All right. And I like this question here. So we're going to go over this one as well. So it says, for each of the following statements, determine whether it is true or false. In each case, explain the reasoning that supports your answer. All righty. I'm going to read this with you, and then I want you to pause this, think it through, and then we'll talk about the answer. If the pH of a hydrochloric acid solution is the same as the pH of a propanoic acid solution, then the molar concentration of the hydrochloric acid solution must be less than the molar concentration of the propanoic acid. So they're asking you to tell me whether it's true or false and then explain. So pause this and then think about it. You don't have to write it down, but think about it, and then we will chit chat. Okay? So really do it, think about it, and then we'll talk. All right. So in this case, if our pHs are equal for HCl and propanoic acid, you should know that HCl is one of our 6 or 7 strong acids. So it is strong. It's going to dissociate 100%. This propanoic acid, because it has a K value that's small, not going to dissociate. We got to do a lot more nasty math with it. But what it's saying in this is it's saying that if the two solutions have the same pH, then the H plus or the HCl solution must be a lower molarity. And that is true. Okay, so it is a true explanation. And so the first thing you're going to do is you're going to answer the question, true. Okay, and then you have to explain why. And so my thought process was that if the solutions have the same pH, they must have the same H plus concentration. I'm going to write H3O plus there. We know that to be true. So the only way they can have the same pH is if they have the same H3O plus concentration. However, since HCl dissociates completely, you could say ionizes, dissociates, breaks apart. It will require a lower concentration of acid than propanoic, which only partially ionizes. So if you think about it, since my acid is going to break apart 100% in HCl, I don't need as much actual acid there, because when it breaks apart, it's all acid. But I'm going to need a higher molarity of the propanoic because it doesn't break apart 100%. So to get the same concentration of ions, I'm going to need a lot more propanoic acid so that I get that H plus concentration being higher. Okay, so this is finding a Ka. If you have any questions, please make sure you get them cleared up. Otherwise, we will see you next time.